Welcome to Part 4 of Lecture 17 for Chemistry 312 Radiochemistry. This lecture is on radiochemical separations, focusing on specific actinide separations. The readings for Part 4 are the same as the previous readings, actinide separation science and technology. In Part 4, we're going to focus on specific actinide separations, neptunium, plutonium, americium, curium. Within that, we'll also discuss uranium separations. These discussions are taken from the previous lectures on the elements, so it's a review section. If you wish, you can speed through or skip this review. However, at the end of this lecture are review notes and example questions which you should examine. We'll now review some separations for the actinides based on what we discussed on overall separations. We'll start with plutonium. Separations of plutonium, obviously from the Manhattan Project. Currently there's about 2,000 metric tons of plutonium that have been produced. The current rate's around 75 metric tons a year. The separated amount, we have a little over 200 metric tons for the fuel cycle and 200 metric tons for devices. So those are some of the current situations on separated plutonium. As we discussed earlier, PUREX is a large-scale processing route for separation of plutonium. As we gave detail on this separation route in earlier lectures, it will not be covered for the plutonium. The first route for separating out plutonium on a large scale is the bismuth phosphate process. This was done during the Manhattan Project, and you get precipitates of phosphate, of bismuth phosphate, in acid. These precipitates carry tri- and tetravalent actinides. So unlike some of the solvent extraction systems where we get tetravalent and hexavalent metal ions traveling together, in this case we get the trivalent and the tetravalent. So one could form this carrier type process with bismuth nitrate and phosphoric acid. You can then precipitate out the solid, separate it, and then achieve any further separations based upon the exploitation of the chemistry. So for instance, with plutonium could be in the 3 or plus 4 oxidation state. Addition of bismuth nitrate or phosphoric acid will drive the precipitation of bismuth phosphate carrying the plutonium 4, along with any other trivalent or tetravalent metal ions, actinides that are present. The plutonium can then be oxidized to the 6, which would achieve a separation of that material. In some forms of the bismuth phosphate process, sulfuric acid forms uranium sulfate, which prevents precipitation of that material in the solution. So one could use that as a route for trying to tune the chemistry of the uranium so that it does not come out with the plutonium. And this method can be used after initial purification methods. For instance, the lanthanum fluoride precipitation for trivalent, tetravalent actinides can first be used to achieve a separation. Bismuth phosphate can then be used to further purify the material, and then an oxidation of the plutonium achieves a separation of the plutonium in this route. As we've already discussed, solvent extraction, plutonium is well known with tributyl phosphate, part of the PUREX process. There's some interest in third phase formation. There's some literature on this and links into the website. Ion exchange and extraction chromatography are also well known for separations of plutonium. These are more laboratory scale separations. Some trends can be based upon oxidation state. So plutonium 3, 4, 5, and 6, imagine they have different oxidation states. And this would be sorption onto a strong base anion exchange resin in HCl. So for instance, the plutonium 3 is not absorbed, and the 4, 5, or 6 are sorbed at different HCl concentrations depending upon their oxidation state. So this could be a route for purifying plutonium by sorbing it to an anion exchanger, reducing it, and upon the reduction to the 3, the plutonium is released. Another example is shown here, where we have some of the different plutonium oxidation states. The plutonium 6 sorption has very high properties on this TRUEX resin. So this would be an anion exchange resin, whereas the 4 also has relatively good sorption properties, but less than the 6. In general, cation exchange trends for plutonium, the nitrates, sulfuric and perchloric acid show stronger influence than the HCl. And there's an increase in distribution coefficients in perchloric at high acidities exhibited for plutonium-3 and plutonium-4. Other separations of plutonium can be based on some of their volatility behavior, like uranium. Plutonium hexafluoride is volatile. This can be a route for separating out plutonium, so producing the fluoride from the dioxide. And then the hexavalent form can be decomposed to the tetravalent form of the fluoride species, which is not volatile. This species can be then removed on this decomposition column. There's also some new work on supercritical fluid extraction. Most research is done with CO2 as a supercritical fluid, but with this supercritical fluid, you have ligands like tributyl phosphate, thionyl trifluoroacetone, and use this to complex plutonium. This has been studied for extraction of plutonium from soils. Okay, this ends the first part of our plutonium lecture. The second part will cover the metals and properties related to nuclear fuel. And some final examples of plutonium separations, reviewing the systems and concepts that we've discussed previously. Alkaline solution chemistry, often not exploited for separations, can be used in plutonium. One would need strong ligands to compete with the hydroxide formation, so fluoride, carbonate, peroxide species of the actinides are certainly known. You can get high stability based upon the higher oxidation states can be achieved with plutonium, and there are also conditions where plutonium-7 can be stabilized, and this compound can be used in this species as a route for separating plutonium from metal ions in a solution. In particular with an alkaline system, so that you can get soluble plutonium species with precipitates of other metal ions. And then finally, a review of what we just discussed with room temperature ionic liquids. There's some quaternary ammonium with anions we've discussed, liquid-liquid extractions as we gave a previous example. And then there's electrodeposition studies, and this is something that's really ongoing and a potential route for forming plutonium metal for both experiment and application purposes. We've already discussed the solvent extraction based methods using tributyl phosphate, where very similar to the uranium, we get the neptunium-6, 2 nitrate tributyl phosphate, and as we'll see with plutonium, the neptunium-4 with 4 nitrates tributyl phosphate system extracted. Data is shown here for the extraction of tetravalent neptunium and hexavalent neptunium. CMPO, which is a ligand that is preferentially used in the TRUEX process, has also been studied with tributyl phosphate, and separations have been achieved with oxidation state variation, where neptunium and plutonium can be reduced and neptunium-4 can be extracted into organic and then removed with the carbonate oxalate, or EDTA. Other neptunium solvent extractions include the use of HDEHP, which is the molecule shown here. This is also part of processing for actinides. In this case, with 1 molar nitric acid with the addition of sodium nitrite, the uranium, plutonium, neptunium, and americium go into the most stable oxidation states. In this case, neptunium-5 is not extracted. So we get oxidized material, we can extract, and then if neptunium is reduced back to the 5, it can be back extracted into 1 molar nitric acid. Trianoctylamine is also used, and this has been exploited for separation of neptunium from environmental samples, where you can extract the neptunium in 10 molar HCl and then back extract it with weaker HCl and a little bit of HF. Combinations of ligands, synergistic extractions with CMPO and tributyl phosphate in dodecane have also been performed. And as we can see here, we can vary the distribution coefficients, so depending upon the oxidation states. And if we examine a system such as 1 molar nitric acid, this mixture of CMPO and tributyl phosphate has a very high extraction for neptunium-6, extremely low for neptunium-5, and above 1 for neptunium-4. So here's a clear example of how the role of the neptunium oxidation state will vary the extraction behavior as a function of acid concentration. The trivalent metal ions, americium and curium, can also be separated, and we'll describe both those metal ions. Tributyl phosphate separations based on solvent extraction of americium can be achieved. Americium could be extracted from neutral low acid solutions with high nitrate. Also, oxidation of americium to the 6th state will achieve a separation, as we discussed. Nominally trivalent metal ions, and what we discussed previously, show that you do not have high solvent extraction. Conditions can be achieved to have the high trivalent metal ion extraction, but with americium, one can make the oxidized americium-6, and then that would achieve a separation based upon the fundamental chemistry of the tributyl phosphate that we described in the PUREX process. In an example of this work, with 100% tributyl phosphate from 1 molar nitric acid, you get wide separation factors of americium from neodymium. Americium separation from the lanthanides have also been performed using 1 molar ammonium thiocyanate aqueous phase, so a complex in the aqueous phase that helps drive the separation. Dibutyl butylphosphonate has also been used. You get the phosphonate functional group. It's similar to tributyl phosphate, so you get a functional group such as that, but it's a stronger extractant for americium. And the trialkyl phosphine oxides, as shown here, are also used. Again, one of the differences between the tributyl phosphate and this molecule is that you're missing the oxygen here in this molecule compared to tributyl phosphate. This increase in the basicity of the functionalized part of the molecule has a way of tuning the extractions compared to the tributyl phosphate, the dibutyl butylphosphonate, and the trialkyl phosphine oxides. Americium and curium extract with this ligand in 1 to 2 molar nitric acid, and studies have been shown that you can have 30% of the trialkyl phosphine oxide in kerosene, and then you can extract the trivalent, tetravalent, and hexavalent actinides, and then you can strip out the americium by treating the organic phase with 5.5 molar nitric acid. Other solvent extractions that are used for americium includes HDEHP. This is part of the TALSPEAK process, which you can look at. You can look up in some links on the separations page, and will be part of the separations presentation. TALSPEAK uses HDEHP, nitric acid, DTPA, and lactic acid. So this organic, the HDEHP, is shown here. It goes into the organic phase. The DTPA, diethylene triamine pentacetic acid, remains in the aqueous phase, and lactic acid is used as a buffer. CMPO has also been used, the ligand shown here, and this is part of the TRUEX process, which is used for fission product extractions. So separation from the lanthanides and actinides from the fission products. And this also employs tributyl phosphate, the CMPO, oxalic acid, lactic acid, again as a buffer, and DTPA. Other extractants that have been evaluated include some amine salts. They've been evaluated in low acid, high nitrate, or chloride solutions. Common extractant is called this aliquot 336, which is shown here. This is useful for extracting in low acid and high salt solutions, and you get an extraction sequence of curium being less than californium, americium, and einsteinium. This has been examined at Argonne National Lab for process separations involving americium, the aliquot 336. There's also a number of amide extractants. The amide functional group is shown here. This is the basis of a process that's been evaluated in Europe called the Diamex process, where this malignamide has been used as part of the Diamex process, and in 3 to 4 molar nitric acid, so now we're at higher acid concentrations, you get a selective extraction of americium over neodymium. Other separations have included separations of americium from the lanthanides with an extraction reaction. An example that's shown here is with Cyanex 301. This compound is shown here. This ligand is stable in acid. And as an example shown here, there's distributions of the trivalent americium and the trivalent lanthanides in 1 molar Cyanex. That's around 16 mole percent of Cyanex 301 in heptane. So you can use this ligand to achieve selective separations, and it's driven by the soft donor properties of these ligands. Radiation studies have also been performed with phosphorus compounds, and extractions start to become problematic at relatively high doses, and this has led to the synthesis and characterization study of other phosphonic acids that tend to be less sensitive to the acid concentration, less sensitive to radiation and hydrolysis effects. However, most of these ligands operate with synergistic extractions, so you tend to have more than one ligand in the solvent system. So, for example, these diphosphonic acids will work with tributyl phosphate, trioctylphosphine oxide, or tributyl phosphine oxide. The aqueous phases are between 0.1 and 1 molar. So the acidity isn't as high as some of the extractants that we saw on the previous page, but they're in a regime which is relatively easy to control. Separation of americium and curium has been examined with ion exchange, and much of this exploits the fact that lithium chloride has shown to separate the actinides from the lanthanides. As shown here, here's an example of 10 molar lithium chloride separation. Distribution coefficients on Dowex resin, we see that the lanthanides have a very low distribution coefficients and the actinides a much higher distribution coefficient. So ion exchange has been used in 2 tracer type levels, one using a displacement complexing chromatography. It involves a 2 ligand system, 2 metals that act as competing cations. You use the slight differences in the complexation between americium and curium to achieve a separation. This method is somewhat cumbersome and complex, can be used on a small scale, but not particularly suitable to large scale separations. Another route for separating americium, curium, and lanthanides is to sorb the material to a cation exchange resin at pH 2. And separation of curium from americium was achieved by using a relatively weak phosphonic acid solution, this ethylene diamine tetramethylphosphonic acid, at pH 3.4 in 0.1 molar sodium nitrate. And you achieved a separation factor of 1.4. Not a particularly high separation factor, but one that could be used to achieve a separation if enough effort is put into the system. Large-scale gram quantity separation of americium curium has been performed using cation and anion exchange, and it's using ligands such as alpha-hydroxy isobutyrate, which we showed was used in the discovery of these elements to separate the lanthanides, and they also are useful in separating the actinides. DTPA can also be used as an organic ligand in this case, where the metal ions are sorbed to the resin and selectively removed with the acids. The eluent can be varied using a gradient of methanol and nitric acid. Best separations were achieved under high pressure. Separation factors can be as great as 400, much larger than the separation factor as we previously discussed. And the use of high pressure increases the theoretical plates of the system, enhancing the separation. Extraction chromatography is also performed with americium. One can think of extraction chromatography as combining solvent extraction and ion exchange, where there's a mobile liquid phase, generally the aqueous phase, and a stationary liquid phase, generally represented as the organic. So for the americium work, you can apply studies that were performed with the organic ligands such as HDEHP, CMPO, aliquot 336, and these are the basis of ichrome resins. There are some limitations in the solution depending upon what sort of ligands you have. These are mainly based upon the fact that these ligands will coordinate strongly with the metal ion, preventing interaction with the resin. There is another resin from ichrome which uses ethylhexyl methane diphosphonic acid on an inert support, and this extracts trivalent, tetravalent, and hexavalent actinides. In fact, this resin binds those metal ions so strongly that there's a need to remove the organics from the support in order to liberate the metal ions from the column. There's also variations of support. The ichrome resins are just hydrophobic interactions which keep the resins on the column. One can also covalently bond molecules to silica, and then some of these sites that it can be covalently bonded, you can coat the particles with ferromagnetic make them have ferromagnetic properties. So after separation, you can use a magnetic field to separate the resins. You can pull out the resins from the solution, thereby separating out any extracted americium. Other aqueous separation processes for americium include precipitation. This is driven by the formation of insoluble americium species, everywhere from trivalent to the pentavalent americium, here shown as the carbonate. Particularly this species, where americium can be oxidized to the +5, where cerium cannot be oxidized, is a route for separating americium from cerium. Americium can also be separated from the lanthanides by oxalate precipitation, where particularly the use of dimethyl oxalate as a route for this selective method of precipitation to achieve 50% lanthanide rejection, with only 4% americium rejection. So in this case, the precipitate winds up being enriched in the americium. Other routes for precipitation include americium-6 and the precipitation of cerium-3. So in this route, the hexavalent state is soluble, where cerium, as a trivalent, could be precipitated by such species as the fluoride. There's also pyrochemical processes for separating americium, particularly from plutonium, where if in a molten salt system oxygen is introduced, plutonium dioxide forms and precipitates. And americium can also be partitioned between liquid bismuth or aluminum and molten salts. I think this could be thought of as a solvent extraction system, where the solvents are molten salt and a liquid metal. Distribution coefficients of 2 for the aluminum system have been achieved for americium. Volatility-based separations of americium from plutonium can also be achieved by exploiting the plutonium hexafluoride, which is volatile. So the formation of this fluoride species in a fluoride salt, so you start with the tetrafluoride of plutonium, bring it to the hexafluoride state, and achieve separation from americium by the volatilization of the plutonium species. Cerium separations are very similar to what we've already described for americium. So this is just a review. Again, tributyl phosphate can be used, not at the high acid concentrations that are useful for plutonium and uranium, but at lower acid concentrations. HDEHP can be used in nitric and lithium chloride systems. CMPO, cerium can be treated similar to what was described for the americium. Ion exchange, again with the lithium chloride, nitric, and HCl systems, where this work exploits the formation of anionic chloride species at the high lithium chloride concentrations. And then precipitations, particularly from americium, can be used by the fact of precipitating out the americium-5 carbonate species. And then any sort of purification based upon precipitation of curium can be done with hydroxide, oxalates, or fluoride, similar to the conditions that were described for trivalent americium. This concludes our lecture on separations. We reviewed a number of different strategies: solvent extraction, ion exchange, volatility, electrochemistry. From this initial study, one should be able to understand how oxidation states influence different separation methods, different mechanisms involved in solvent extraction, and then some discussion about specific actinide separations, which we just went over. You should be able to describe components of ion exchange resins and, for instance, provide a separation. For example, if one was asked how would one separate americium from neptunium and uranium, one could achieve that separation and should be able to describe it based upon what we've presented, or additionally find out where the information is to get more details. And here are some questions related to Lecture 17 on separations. So describe the concepts in solvent extraction. Well, solvent extraction is a two-phase system. We've got an aqueous phase and an organic phase, and generally the ligand is in the organic phase. So you adjust the aqueous phase with a specific ligand. You form a metal ligand complex which is neutral, and that goes into the organic phase. So by this way you separate a specific metal ion, usually by oxidation state, from an aqueous phase into an organic phase. And you tune your system so that only the metal ion that you're interested in goes into the organic phase. So what is a distribution coefficient? Again, this is a term that's used in organic phase and aqueous phase distributions, so solvent extractions. And what it is, it's the concentration of the metal ion in the organic phase divided by its concentration in the aqueous phase. So KDs that are large means that the metal ion migrates from the aqueous phase into the organic phase. You should be able to describe the PUREX process, and the PUREX process is a route for separating plutonium from uranium and other actinides and fission products. And this is achieved by taking material, generally the oxide of uranium that has been irradiated, so you have plutonium in that system. It's dissolved in nitric acid. The nitric acid is adjusted to 3.5 molar. And the PUREX organic phase is tributyl phosphate and kerosene. Upon contact, the uranium-6 and plutonium-4 are extracted into the organic phase. Phases are separated. The organic phase can be washed, and then it's contacted again with a 3.5 molar nitric acid phase, but this time with a reductant. The reductant can be something on the order of uranium-4 or iron-3 or hydroxylamine nitrate. This reduces the plutonium from the 4 to the 3, which is no longer soluble in the organic phase, and the plutonium-3 then moves to the aqueous phase where it can be separated from the uranium. And how are separations performed on a resin? For separations being performed on a resin, one would have an addition of a solution to a column. The metal ion of interest would have a large sorption to the column. The solution can continually be passed through. Those metal ions that do not sorb to the column are then separated. They go out with the solution phase. And then you can adjust your solution phase to remove the metal ion from the column. So for instance, one could sorb a metal ion. You can absorb an anion exchange. You can use an anion exchange column. High acid concentration, high nitric acid concentration. You can get something like uranyl nitrates sorb to the column. It would sorb onto the anion exchange resin, reducing the acid concentration, reduces the nitrate concentration, and the uranium is no longer anionic. It can form neutral species, which then remove from the column. What are theoretical plates for chromatography? Well, in chromatography separations, we discussed the idea of theoretical plates, and they're fundamentally, you can think about them as fractions within the column where the exchange chemistry occurs. The more theoretical plates one has in a column, the higher the separations that can be achieved. So this is something that's one of the reasons why high-performance liquid chromatography is used, because that increases the number of theoretical plates on a column. And what volatile form of plutonium can be used in separations? Well, just like uranium hexafluoride, plutonium hexafluoride is volatile and can be used in separations. Additional questions are shown here. For example, what type of group separations are possible with molten salts? By examining the free energies for the chlorides, we see that the metal ions tend to break into certain groups. For instance, the higher free energies tend to be noble metals. Then there's a group of iron to zirconium. Then there's another gap here with the actinides and the lanthanide elements. So the actinides here, lanthanides here. And then group 1 and 2 elements have the lowest free energies. In other words, they tend to remain in the salts the longest. And how would one separate uranium, plutonium, and americium with an organic phase that's 0.5 molar HDEHP and isooctane with a nitric acid aqueous phase? Well, one could look at some data, as was shown here, where we have the distribution coefficient plotted against the log of the nitric acid concentration. And here are some oxidation states which are common. So we have the trivalent americium, the hexavalent uranium, and the tetravalent plutonium. If one were to take this as, let's say if we had the uranium, plutonium, and americium as a solid, and we picked it up in 10 molar nitric acid, so this is a log scale, we could then contact this solution with our organics. The uranium and plutonium would then extract into the solution. The americium would remain in the aqueous phase. So this would give us our first separation. So now we'd have americium in the aqueous phase primarily, and uranium and plutonium in the organic phase. So now to separate the plutonium from the uranium, changing the acid concentration doesn't have a strong impact on the distribution coefficient. Both the uranium and plutonium values are much greater than 1, regardless of the acid concentration. So what one could do, we know that in the PUREX process, plutonium is reduced, so do the same thing here. Drive plutonium from the 4 to the 3. One doesn't have the data here, but one could guess that the plutonium 3 is going to act a lot like the americium 3 and extract. So even if you had it in the 10 molar nitric acid system and you reduce the plutonium from the 4 to the 3 in that system, it would come out of the organic phase and into the aqueous phase. So a simple route for separating these three elements would be to pick it up in 10 molar acid, contact it with the organic phase, pull off the aqueous phase that contains the americium, then reduce the plutonium from the 4 to the 3, and it would come out. So you'd have a relatively simple route for separating out these elements.
When you have completed the fourth part of Lecture 17, please comment on the blog and respond to the Lecture 17.